So in this lesson, we'll be discussing linked acceleration. That is acceleration when we have objects connected to one another. So generally in many mechanics problem, we often encounter questions where two or more objects are connected together. Usually, this connection is done using inextensible strings passing over a smooth pulley. Okay, we used to have something like this, where we have two objects passed over a pulley. Okay, and then the system is attached to a rigid support. Sometimes we could also have two objects positioned in this form. Let's call this one, this is case A, this is case B, this is case C. There are other cases, but let's look at these three first. So in this case B, mass M1 and mass M2 are connected over a smooth pulley. And while mass M1 is sitting on the table, while mass M2 is dangling. And in case 3, we have an inclined plane where the first mass is sitting on the plane and the second mass is dangling. So how do we, so because of this relation, we will definitely have acceleration that is linked. Okay. Now, but before delving deep into this concept, there are some very important key terminologies that we need to discuss. Some of those terminology, first, what is linked acceleration? When we say linked acceleration, what are we talking about? So linked acceleration. So when we say linked acceleration, what we really mean is it's a common acceleration that is experienced by two or more connected bodies due to the force acting on them. Just as what we have seen here. Because of the fact that these two objects are connected, okay? If there is variation in the masses, especially in this first case, we are going to have an acceleration. The object is going to accelerate to the part that has the heavier mass. Okay, if the masses are the same, for example, in this case A now, if the masses are the same, we do not expect an overall acceleration because the masses are the same. So the total forces surrounding this place will balance the total forces around this place. So there won't be acceleration. But however, what about in the case where M2 is greater than M1 or M1 is greater than M2? In that case, we'll have what? An acceleration. So say that common acceleration. And if we have varying masses, the acceleration with which M1 is going to move is the same M2, is the same acceleration with which M2 is going to move. So let's take a case study now. Let's say M1 is greater than M2. If M1 is greater than M2, meaning that M1 is going to pull M2. So M1 accelerates downward while M2 accelerates upward. However, the two acceleration will be the same. So that acceleration is going to be is a linked acceleration. So the acceleration of mass M1 is going to be the acceleration of mass M2. So that's the first concept, the concept of linked acceleration. Now, another concept that must be very clear is the concept of tension. So when we say tension, because those are the terminologies we use as we move on into the concept. Now, what do we mean by tension? So we say tension is like is the pulling force transmitted through a string, a rope, or a cable. For example, let's go back to this system. Looking at this system, as the mass of this object, of course, the weight of an object will always act downward. As the weight of this object acts downward, there will be a reaction experienced by this rope, okay, which will be equivalent to the weight of this mass, of this object that we have here, according from Newton's third law, for every action, there will be an equal and opposite reaction. So if this weight is 20 Newton, then we will experience a tension of about 20 Newton in this rope, assuming let's assume there is no mass M2 present. So the idea of tension means the pulling force that is transmitted through a particular string. Okay. So another important term that we also need to deal with is we are going to be assuming that the string of connection is an inextensible. It is inextensible. Inextensible, in other words, it means the string does not stretch. It does not stretch. So it's very, very important. That is, the string of connection of the bodies of the masses are inextensible. Okay, the strings here connecting mass M1 and M2 here is inextensible. The string connecting M1 and M2 here is also inextensible. So and also for the third case, the string connecting M1 and M2 is also what? It's also inextensible. So that's another very important concept that needs to be very clear when dealing with linked acceleration of connected objects. Also, another very important concept is the pulley. We also assume that we are dealing with a what? With a smooth pulley. Okay? That is, what do we mean by a smooth pulley? A smooth pulley is one that has no friction. Okay? That is, we are assuming that there is no friction imposed by that by the pulley, meaning that the tension that is experienced on this side will be exactly the same as the tension that will be experienced on this side. There will not be loss of any force anywhere because the pulley is assumed to be frictionless. So there's no force lost due to the frictional force. Okay. Another very important term that we also need to be very clear about is that the string is also assumed to be light, a light string. Okay. That is, what do we mean by the string is light? That is, it has negligible mass. A negligible mass. So the mass of the string is not contributing to the overall weight of the masses we have in the system, either on the left or on the right. So all these concepts must be very, very clear before we delve deep into linked acceleration. Now, we're going to pick each of these systems one after the other, and we are going to analyze them so that we can fully understand what is happening in each of these cases. So now let's start with this first case. Now, for the first case, what do we have? We have a system. Let's call this one case 1. So the case 1 we are going to be considering. In this case 1, let's assume that mass M1 and mass M2 are the same. Let's say mass M1 is equals to M2. If mass M1 is equals to M2, what is the consequence of that? The consequence of that is that the downward force here, that is the weight of this first mass, let's call this one, this is our mass M1. The weight of this mass M1 is going to be M1 times gravity. Of course, if you remember, you know that weight of an object is mass multiplied by acceleration due to gravity. Our acceleration due to gravity, which is W is equals to what? Mg. Okay, so for the first mass, the weight is going to be M1g. While for the second mass, the weight is also going to be what? M2g. Now, if M1 is equal to M2, so what does that imply? It implies that the weight, the total weight that will be experienced on the left and the one that will be experienced on the right, it will cancel out. So in this kind of system, our acceleration will simply be 0 because the system is going to remain at equilibrium because we are going to experience what? We are going to experience equilibrium. So that is the first case where our masses are what? Are the same. Now, let's look at another case. In a case where let's look at the case where M1 is not the same as M2. Let's assume in this case, M1 is less than M2. So if M1 is less than M2, let's call this one our case 2. So if M1 is less than M2, meaning what that means is, for example, let's say M2 is about 10 kg, while M1 is about 4 kg. Then what will be experienced is that we are going to experience an acceleration towards M2, meaning because M2 is now greater than M1, it means the system is going to accelerate this way. Okay, while this object moves upward, this one moves downward. However, because it is an inextensible string, passing over a smooth pulley is what we are using, then the acceleration, the upward acceleration here will be equal to the downward acceleration experienced by M1 and M2 respectively. So in that case, let's do something now. Let's write a force balance around each of the masses. Let's write a force balance around each of the masses. Force balance around mass M1. Force balance. Let's just call it force balance. Although let's just say force around M1. Okay. Of course, since M1 is accelerating upward, M1 is accelerating upward, it implies that the upward force is more than the downward force. So meaning we can say the tension in the string, okay, minus the weight of that object, which is M1G, will be equals to the equivalent force, the total force around this object, which is going to be F. Okay, but this F is nothing but what? The mass of that object M1 times its acceleration. So in that case, we can say we have T minus M1G equals to M1A. We can call this one our equation 1. Now let's do the same for mass M2. So since we are assuming that M2 is greater, meaning that the total downward force is more than the upward force. So we could say our M2G minus the upward force T is going to give us the F of the second force. Let's call this one F2. Let's differentiate between the 4. This is F1. So this F2 is going to be what? The second mass multiplied by what? Sorry, multiplied by acceleration. Multiplied by acceleration. That is our M2G minus tension is equals to M2A, and we call this one our equation 2. So observing closely, we see that we now have two equations, equation 1 and equation 2. And we could just add equation 1. If you add equation 1 to equation 2, we'll be able to eliminate the tension. And in that case, we see that we are going to get our tension is going to eliminate. Then we have M2G minus M1G to be equals to M1 plus M2A. Since we have M1A here, we have M2A here. A is common, and we can factorize the A out. And from here, we can summarize and see that our acceleration, if we divide both sides by M1 plus M2, we'll be able to establish that our acceleration is going to be M2, we see that G is also common here. We can factorize M2 minus M1 times G divided by M1 plus M2. So this gives us what? This gives us the acceleration of the system when M1 is less than M2 in mass. When M1 is less than M2 in mass. So with this, we can also quickly derive an expression for the corresponding tension that will be experienced. Now, from either of the equation, either equation 1 or equation 2, let's go to a fresh page. From our equation 1, we have tension. We have our tension T minus M1A, referring back to this equation 1. Let's use equation 1. T minus M1G is equals to M1A. T minus M1G is equals to M1A. From here, we could see that our tension is M1A plus M1G, which implies that our tension is actually M1 into bracket A plus G. Okay, so if acceleration is known, okay, adding it to the acceleration due to gravity, then we multiply by the mass M1, which is the lighter mass. Okay, we are going to get our tension. But now let's just do some maths here. Is it possible for us to just substitute the value of acceleration? Since our acceleration has been established to be M2 minus M1 over M1 plus M2 times G, can we do some substitution here to get something interesting? Yes, I think it can be done. So we can say T is equals to M1. Let's put our value of acceleration, which is, what do we have? We have M2 minus M1, M2 minus M1 times G. Okay, let's put a bigger bracket here, all over M2 or M1 plus M2. This is the value of acceleration A that we got. Then we add G to this, adding G to this. Okay, from here now, let's see if we can tidy this up and get something interesting. We could do some, let's do our LCM here. From here, we see that we have the LCM is going to be M1 plus M2. Okay, we still have our M1 as a coefficient outside. Then from here, we have M2. Let's open up this M2G minus M1G added to G into bracket M1. Okay, we could just get that one directly. We get it as M1G plus M2G. Okay, then looking closely, we'll see that we have minus M1G plus M1G. So this can cancel out and we'll get 0 there, such that what we will be left with now, we're going to get M1, and we have M2 here. So we have M1, M2, we have M2G plus M2G. That gives us 2M2G. So we have this one times 2M2G all over M1 plus M2. Okay, meaning our tension, the tension can be gotten by doubling the product of M1 and M2 multiplied by gravity and dividing by the sum. Dividing by the sum of M1 and M2. So we have derived an interesting expression that can be used to calculate the tension that will be experienced in the inextensible string. So we have our tension to be T equals to 2M1 M2G over M1 plus M2. And we have already established our acceleration to be, our acceleration to be A is equals to m2 minus m1g all over m1 plus m2. Okay, let's put this one also in the box. So this is the derivation for a string that is connected, two masses that is connected using an inextensible string passed over a smooth pulley on the condition that M2, the condition we are dealing with here is that we are assuming that our M2 is greater than M1, or you say M1 is less than M2. So this is the first case. The second case where the M1 is greater than M2, or you say M1 is less than, M2 is greater than M1, or M1 is less than M2. Okay, nothing far-fetched. If we have assumed M1 to be greater than M2, it's just, all it means is that the masses will switch places, and it will still, we'll still be able to use the same formula to evaluate whatever we want to evaluate. So having done that, we can move on to the second case. In the second case, we have two masses. One of the masses sitting on the surface, let's say a table. Usually, in the general case, we are going to assume that the table is not 100% smooth. That is, there's some coefficient of friction present in that on that table. Okay, and if there is some coefficient of friction, it implies that we are going to have some frictional force. So we're going to pick this second case now and analyze it. So let's pick this second case. Okay. Now, let's assume we have this now. First, before we delve deep into this, we need to, let's look at some foundational concepts that needs to be very clear. When we have a surface, okay, when we have a surface and we have an object sitting conveniently on that surface, okay, of course, we know the weight of the mass. Let's say we have a mass, the object is of mass m. This object is going to have a weight of m1 multiplied by gravity. Okay, from Newton's third law of motion, for every action, we have equal and opposite reaction. So on this same surface, we are going to experience a reaction R, which will be what? Which will be equals to mg. That is, the weight is the action here, having a value, a magnitude mg. The reaction also will have a magnitude mg. So if this system experiences a pull, okay, there is the force that is just enough to make this object to leave its position is called the frictional force. Okay, so from here, we know that the frictional force, okay, is always proportional to reaction. Okay, so in this case, our frictional force is going to be equals to our coefficient of friction multiplied by that reaction. So from here, we see that our frictional force is nothing but mu mg. So we need to keep this at the back of our mind, that the frictional force can be computed by saying the coefficient of friction, or coefficient of friction multiplied by mass multiplied by gravity. That gives us the frictional force. And the frictional force is always in opposition to the direction of what? To the direction of motion. So having established this interesting concept, having established this, let's look at, now let's come back to this part. Of course, This M2 is going to experience a downward force, a downward weight, of course, force, which is M2 multiplied by gravity. Then we are going to have a tension T, which will be equal to the tension in this string, since it is an inextensible string and there's no friction in the pulley, imposed by the pulley. Also, we are going to experience some frictional force due to the roughness of the table. Okay, so because of this, we can write the total force surrounding this object sitting on the table. From here, we'll see that for this table, we are assuming that this object is going to accelerate downward. Okay, for this table, for this object on the table to move in this direction, it implies that the T1, let's use a white ink, the T1, our tension minus the frictional force is going to be the force with which this object is going to move, which will be equals to what? Which will be equal to our M1 multiplied by its acceleration. And having known that our F1, our FR is what? T minus mu, let's say it's going to be mu M1G, since our mass from what from our derivation is going to be mu M1G equals to what? M1 times acceleration. So let's say this one is equation 1. Then the second equation, we have around the second mass, we see that the downward force, that's M2G minus the tension, is going to be equal to the overall, the equivalent force, which is M2 times acceleration. We can call that one equation 2. So the same thing we did in the second case, we can also do it in this third case, because this is our third case 3. We can sum up equation 1 and 2, add equation 1 and 2. If you had equation 1 and 2, what do we have? We're going to eventually have M2G minus mu M1G to be equals to our M1 plus M2 times the whole acceleration, since the acceleration is common for this case. So from here, we could also establish, if we divide both sides by M1 and M2, we'll see that our acceleration can be gotten to be M2G minus mu M1G all over M1 plus M2. Okay. Now, if we also look closely, we see that G is common on both sides. Then because of that, we can remove this G. We can remove this G here and just factorize it out, since it is common to both terms here. So we can just remove it and put it outside the bracket, so that we can have a new relation for our acceleration. Okay. So this gives a relation for the acceleration, the linked acceleration for the two objects passed over a smooth pulley, with one sitting on the table and the other one dangling. Similarly, we could also, let's try to evaluate the tension using this acceleration, using equation 1, the way we did for the second case. Let's do that. Okay, let's go to a fresh page. From our equation, we have tension. Our tension is T minus mu. We have the equation to be T minus mu M1G equals to M1A. Okay. T minus mu M1G equals to M1A. Okay. We want to eliminate A. So we can take this one to the other side. So we have T to be equals to M1A plus mu M1G. Okay. We could do the direct substitution from here, or we could factorize M1 out first. Whichever case, it will still work. Okay, let's also factorize M1 out first, so that we can have M1 into bracket A plus mu G. Then we put in the derived acceleration value, the acceleration that we derived. So we have our M1. Let's use a bigger bracket here. Okay, then we have our acceleration to be m2 minus mu m1g. Okay, we have our m2 minus mu m1g all over, this is in brackets, all over m1 plus m2. Then we have addition with mu g. Okay, let's confirm, let's cross-check that once before we move on. Our acceleration is m2 minus mu m1, not m2, m1. So what we have here is going to be m1 and not m2. So we have m2 minus mu m1g all over m1 plus m2. So let's tidy this up. Tidying this up, we see that we have our m1 still outside the bracket. Then we can also take the LCM here. The LCM here is m1 plus m2, so that we have m2g minus mu m1g. Then this gives us plus, if you open up this bracket, if you do this, we have m1 mu g and plus m2 mu g. Let's put the overall bracket. Then we close the bracket here. Then from here, we could see that we have minus mu m1g plus mu m1g. Mu m1g is the same thing as mu m1 mu g. So this, we eliminate this. Hence, we are going to be left with what? Our tension is going to be m1 into bracket m2g plus m2g plus m2 mu g. So we have m1 into bracket m2g plus m2 mu g. Okay, all divided by m1 plus m2. So which in turn, you see that m2g is common on both sides. So we can have our tension to be m2 can be factorized out, m1, m2, then g is also there, m1, m2, g into bracket 1 plus mu. That's what we're going to have left. Divided by what? Divided by m1 plus m2. So this gives us the tension in that case as m1 m2g into bracket 1 plus mu, which is our coefficient of friction, divided by m1 plus m2. This is for a case where our acceleration is m2. Our acceleration has been gotten to be m2 minus mu m1, m2 minus mu m1 into bracket g over m1 plus m2. So this is for the case of two objects connected, one sitting on the table while the other one is dangling freely, and there is some coefficient of friction experienced between the body. So in a case where there is no coefficient of friction, let's say the table is perfectly smooth. Okay, that's another special case that we can have here. If the table is perfectly smooth, it means there is no coefficient of friction. And if there is no coefficient of friction, this term becomes 0. Then our formula will reduce to, so that is in a case where if mu, okay, if coefficient of friction is 0, that is smooth surface. Okay, if it is smooth surface, meaning our acceleration now reduces to m2g over m1 plus m2. Okay, and similarly, the tension also will reduce to m1 m2g over m1 plus M2 by putting 0. If you put 0 here, you get this. Okay, so that is when the system is what? It's perfectly smooth. Okay. Now, for the last case we have now is the case of when the plane is inclined. When the plane is inclined, that's case, this other case. Okay. So let's take this third case when the plane is inclined. So when the plane is inclined, what do we have? Let's look at that. Now, in this case, also, before we look at this, let's also look at some very interesting concepts around this. Now, naturally, when we have an inclined plane, if you have an inclined plane, okay, there's something interesting about it in the sense that when we have an inclined plane, let's say it is inclined at an angle theta, okay, because of the inclination of this plane, there's also, as the plane implies, if the plane inclines at an angle theta, the normal reaction that is experienced, because normal reaction is always perpendicular to the surface, the normal reaction will also equivalently experience another inclination from its original position by an angle theta. As the plane is inclined, the normal reaction is also inclined at that same angle theta. So the consequence of that is that our normal reaction now to the surface will not be exactly the same as the weight of the object. While we know that the weight of the object will act downward, which will be equals to mg if the mass of this object is m. Okay? Now, this object will experience a downward force, the downward force due to the inclination, okay, which we can say it is equivalent to, if you complete this triangle, we can say that part is going to be our force that will naturally tend to pull this object downward. While our normal reaction can be said to be the other side of this triangle. So we can say this place is our R. Let's call this place our FR. Okay. So we are assuming that, let's assume the object is being pulled upward. Then we'll be experiencing a downward force that will tend to reduce this upward force. Okay. Because of this, you see that there's a relationship between the weights, this FR and R. What is the relationship? The relationship between the R and W now, because this W will be acting like our hypotenuse. Why this place? Because this place is going to be 90 degrees. So from here, we'll see that the cosine of theta will be equal to the adjacent over the hypotenuse. Our adjacent in this case is our R, and our hypotenuse is our W. So from here, it implies that W, or our R, is nothing but W cos theta, which is the same thing as saying mg cos theta. Okay, so similarly, we can do the same thing for sine, for the sine relationship, the relationship between FR and W. So we say that our sine of theta is going to be the opposite, which is FR over W, which implies that our FR is W sine theta, or we call it mg sine theta. So there will be a natural tendency of this object to slide downward, and that lateral tendency is mg sine theta, that force with which it will slide down. Okay, so when we have an inclined object in this case, okay, the point is this object is going to slide down by mg, let's say m1g sine theta. While the tension in this string is T, and the tension in this string is also T, then this one will experience its own downward weight. That this dangling force will experience a downward weight, which is M2G. So because of this, we can write force around each of these masses. From here, similarly, the same way we have done for the case of the surface without inclination. What do we have in that case? We have T. We have our T minus M1G sine theta will be equal to what? Will be equal to M1A. And we also have M2G minus T will be equals to M2A, equation 1 and equation 2. So also we can add equation 1 and 2. If we add equation 1 and 2, we're going to have M2G minus M1G sine theta, okay, will be equal to M1 plus M2 into bracket A. Observe that our G is present on both sides, so we can factorize it out and have our A, and divide both sides, we have our A to be M2 minus M1 sine theta, everything multiplied by G, all over M1 plus M2. So this gives the relation to calculate the acceleration of the object of our system, the linked acceleration of the system where we have an inclination, where the M1 is sitting on the surface and M2 is dangling. So similarly, we can also establish the formula for the tension. Okay, so we can get our tension. Let's just go down here. So we'll see that even if you look closely, you see that what we have in this particular case and the one we had in the earlier case, they are very, very similar in the sense that if you try to evaluate the tension, let's try to evaluate the tension, or let's just write the value. Very simple. The tension is going to be equal to just replacing anywhere we see mu in the previous function, we replace it with what? With sine theta. That is, this is the one we had earlier. Okay, this is one we had earlier. So it will be exactly similar, only that well, in the new case now we have sine theta here, but in this case, former case, we have mu here. Okay, so we can just simply write our tension as this, as exactly this. Okay, let's capture this. Let's capture this. Position it here. And position it here. So what we just need to do is, this is exactly what we are going to have. However, let's take away this line. Let's take away this line. Okay, instead of going through the entire derivation once again, we can just replace this with sine theta. We'll replace this one with sine theta. And that gives us the required derivation for this kind of system where it is connected over an inclined pulley. Let's write the acceleration right beside it. So the acceleration is A equals M2 minus M1 sine theta, all multiplied by gravity divided by M1 plus M2. So this is what we are going to have. Okay. So go through the derivation step by step. Okay. If there is anything, let me know. If you are watching from YouTube, let me know whatever questions you have in the comment section. And if you want me to create solved examples on this, also let me know, and I will do just that. So we're going to stop here. So don't forget to subscribe if you have not subscribed, and share the video with your fellow colleagues or anybody that you feel like is going to benefit from this from this concept. So thank you very much. See you in another class.